Good afternoon. Welcome to Krishna's classroom. The theme of this talk is the concept of first and second category sets and a reformulation of the Bayes category theorem a Bayes theorem in terms of the category sets. Okay. Now let us briefly recall what all things we have done. And in fact, we had a detailed discussion of Bayes theorem in the last lecture. So we just recall some of these aspects. So first we talk about Bayes theorem. Bayes theorem. What you have is this X, a complete metric space. Completeness is the central concept that is at the heart of Bayes theorem. Now suppose the collection Vi be a countable collection of tens dense open sets in X. Then intersection is dense. Now this is what we have proved. Okay? So if X is a complete metric space and this is a countable collection of dense open sets in X, then their intersection is density. Now this is the property that we have proved last time. Now you see that just recall a small thing. Suppose the completeness is not assumed. Then what you can prove is this: if V1, Vn are not assumed, Vn are a finite collection of open sets, dense open sets, next then what you have is this intersection Pi 1 to n. This is a finite intersection. This is non-empty. Now this is what you can prove. But this completeness, in the absence of completeness, you can make a statement only about finite intersections. The remark in the absence of completeness. We can only have finite connection of dense open sets in a dense having a dense intersection. So the connection is this. Completeness is not there, then we can only talk about this, right? And this is not true. And we'll give an example. So the following example. The following example gives an insight I will take the example. Let x be equal to set of all rationals which is enumerated as etc. which is enumerated as q1, q2, q3, etc. Okay. Now what we do is we define take the singleton qi, take the complement of that. That means all elements other than qi. Okay. Now you can show that then vi open now clearly intersection I is equal to 1 to infinity is the countable intersection of vi is. That's very easy to see from this example. Therefore, you see that you cannot, the completeness is important property of metric spaces for a countable collection of dense open subsets to have a dense intersection in X. Okay, so that is something that we observe. Now, we have also seen a generalization of this in the Baire's theorem. You can have a more general version by replacing openness with the G delta problem. Okay. And that we have explained last time. Bayes theorem. If X is a complete metric space, and etc. are a countable collection of G delta sets, then intersection Gn G delta set. That means these open sets can be, open dense subsets can be replaced by countable collection of, or a countable collection of G delta sets, dense okay. So you see that what is a G delta set? G delta set is a countable intersection of open sets. You know that finite intersection of open sets is open, but one cannot make that statement about a countable collection of open sets. Okay, right? Whereas arbitrary union of open sets is open, finite intersection of open sets is a not countable collection of open sets. Countable collection of open sets may not be open. For example, in R, you take Vi or Vn equal to the open set minus 1 by n. Then look at this. You take intersection Vi equal to 120 Vn. Then you know that this is equal to just the singleton 0. And this is not dense in okay. I think this example is not appropriate. Okay, so this is the general result that you have. I don't want to suddenly we can look at an example. The example I gave is minus 1 by n to 1 by n is not dancing x. We can modify that. Now we introduce the notion of what are called categories. Need certain specialized terminology to talk about first category set and the second category set. First we define what is called a knower dense. Definition. A set E is said to be knower dense if E closure contains E closure contains no non-empty open subsets. Subset of no non-empty open subset of that is E closure as an empty entity. This is the criteria for E to be a knower dense set. Okay. Example highlights examples. Equal. Now you take Z, set of all integers now this is knower density. Okay, that is one observation that see. Second example is suppose you take x equal to r and consider q. Then q contained in r is not a knower dense. Or to take Q closure equal to, and this is lower dense. This is in fact it's a whole of R. Therefore, it is certainly dense. Okay. Therefore, Q is not so. If you take the set of all integers, they form a lower dense collection. Whereas if you take Q, this is not a lower dense set. Okay. Now we define what are called first category sets. Because we use this notion of lower dense sets in the definition of first category sets. A first category set. A set is called a set of first category. It is the countable union lower countable is lower dense sets. Okay. Right. Now we will give a quick example. For example, you take set of what? Integers. Then this is of first category because this can be written as union of and each one of this is a singleton element. Each one of this is lower dense. Over. So that is one example. Second example is two. Two is not a first category. Sorry, two is a first category. Earlier we have seen that two is lower dense. Because 2 can be written as again, where 2 can be written as so each one of these is a lower dense and it's a countable union of lower dense, but the countable union, this is not lower dense. So 2 is okay. Lower dense is not, because you take Q closure is equal to Kollam, whereas if you take a singleton and take its closure, it is going to be okay. So this is the so you have examples here. First category, 2 is a set of first category, although it is not lower. Now we do the version of this. Further definition, second category. A set second category. If it is not part of first category, that is all non-first category non-first are sets of second category. Now we give the version of Baire's theorem. So it is called base category. No complete metric space is of first category. That means you have a complete metric space, it is of second category. So let us give an outline of the proof connected with the earlier. So let X be of first category. But complete. X first category implies there exists a countable of lower denses such that X equal to Xi. Now X complement empty. Okay. And this can be written as intersection second. Let's just take the complementation. Yes. Okay. Now Xi complement is So what you get would be that if since X is complete, it intersection one thing say complement. This is not. And see, you get empty set equal to intersection is, and this is non-empty, and therefore there is a correlation. So this is a correlation. The contradiction is this. Why? And this is non-empty. Because this is the closure of this is dense in. Okay, therefore this is not. So this is a contradiction. This is a contradiction. Which implies no category. So we have used Baire's theorem. Okay. So that proves that. Okay, I think I'll conclude here. And then we had been concerned only about metric spaces as far as Baire's theorem is concerned, because it's a theorem that is set in the general setting of a metric space, not necessarily in the case of a Banach space. In Banach spaces, we have this completeness property, and therefore some places where we can effectively apply this set. That is the reason we have explored this theorem, because this is only a tool in the context of proving some of the important structural results in Banach spaces. Okay, thank you.